You know, inside every single one of your gadgets, whether it's your phone or your laptop, there are these tiny, unsung heroes working around the clock to manage power. We call them DC to DC converters. And today, we're going to pull back the curtain and see how these circuits literally make our modern world possible.
So, let me ask you this. Ever stop to think about your laptop? It's got one battery, right? Puts out maybe 12 volts. But the processor inside, that needs a measly 1.2 volts. The screen needs something else. The USB ports need a rock-solid 5 volts. So how on earth does one power source feed all these different parts? Well, that is the exact problem DC-DC converters were invented to solve.
But before we get to the really clever solution, we have to understand the problem. Because the first try at solving this was, well, let's just say it was clumsy and super inefficient.
Yeah, the old school way used something called a linear regulator. The best way to think of it is like a simple valve on a water pipe. If you have too much voltage or pressure, it just clamps down and burns off all that extra energy as heat to get you the lower voltage you need. I mean, it gets the job done, but this kind of brute force approach has a massive, massive drawback.
And that drawback is just a staggering amount of wasted energy. Let's say you're in a really common situation, taking a 12-volt supply down to 5 volts. The efficiency can be as low as 38%. Think about that. That means for every bit of power you put in, you're just throwing away more than 60% of it as useless heat.
The researchers at Rohini College of Engineering didn't pull any punches when they wrote about it. They called it pathetic. And they're right. In a world full of battery-powered gadgets where every little bit of power counts, that's just not going to fly. There had to be a better way.
And thankfully there is. So let's meet the hero of our story, a specific kind of DC to DC converter called the buck converter. This is the smart, super efficient way to step down DC voltage.
So what is a DC-DC converter at its most basic level? Well, it's a switched mode circuit, and that word switched, that's the absolute key. Instead of just burning off power like the old regulators, it uses a high-speed switch to chop up and basically rebuild the electricity, changing the voltage with almost no energy loss.
And here it is. This is the basic circuit. What's so amazing about it is just how simple it is. It's really just made of 4 key parts: a super fast switch, an inductor to store energy, a diode to make sure the current only goes one way, and a capacitor to smooth everything out at the end.
So, how in the world do these 4 little parts work together? Well, the magic isn't in burning energy. It's all about storing it and then releasing it in these perfectly timed little packets.
The secret sauce here is a technique called pulse width modulation, or PWM for short. Okay, imagine you're trying to control the water from a hose. Instead of turning the valve halfway, imagine turning the tap full on and then full off thousands of times a second. By controlling how long the tap is on versus off in each little cycle, that's the pulse width, you can control the average amount of water coming out. That's exactly what a buck converter does with electricity.
It all comes down to a really fast 2-step dance. First, the switch is on. Then, the switch is off. And this happens over and over. Let's break down what's actually going on in each of those 2 phases.
Okay, phase 1. The switch flicks on. Electricity starts flowing from your battery through the switch and into that coil of wire, the inductor. The inductor immediately starts storing this energy, building up a magnetic field. Think of it like charging up a tiny magnetic battery. At the same time, some of that current is also going straight to the output.
Then phase 2. The switch flicks off and the input from the battery is cut off. Now, this is the magic moment. The inductor's magnetic field collapses, releasing all that stored energy. Inductors hate changes in current, so it forces that energy out to keep electricity flowing to the output, using the diode as a path. All of these rapid-fire energy pulses are then smoothed out by the output capacitor, which acts like a small water tank, making sure your device gets a perfectly smooth, stable, lower DC voltage.
So the buck converter is awesome for stepping voltage down. But what if you need to step voltage up? Well, it turns out this simple design is just one member of a whole family of converters.
And this, to me, is the most elegant part. By using those exact same 4 components, the switch, inductor, diode, and capacitor, we can solve completely different power problems. And how do we do it? We just change how they're arranged. The layout of the circuit, the topology, is what decides what it does.
And just look at this, it shows you exactly what I mean. On the left, that's our buck converter, it steps voltage down. On the right, that's a boost converter. Look closely, it's the same parts, they're just shuffled around. And that simple change in the layout completely flips its function, letting it take a low voltage and boost it up to a higher one. It's like electronic Lego.
So there's a whole toolkit of these things for engineers. You've got the buck to step down, the boost to step up. Then you get fancier ones, like the buck boost, which can go either way but also flips the voltage to negative, which you might need for certain sensors or displays. Each one is just a different arrangement of the same basic building blocks, each one tailored for a very specific job.
Okay, so this is all really cool engineering, but why does it actually matter? Well, because without this kind of efficiency, the portable, powerful electronic world that we all live in, it just couldn't exist.
Let's just go back to that efficiency number for a second. Look at this chart. Where that old linear regulator was just torching over 60% of the power as heat, a modern DC-DC converter can easily hit 95% efficiency, sometimes even higher. This isn't just a small improvement, it's a game-changing leap. It's the difference between a phone that gets scorching hot and dies in an hour, and one that stays cool and lasts you all day long.
So where are these hidden heroes? Well, once you know to look for them, you realize they're absolutely everywhere. They're all over your computer's motherboard, feeding those precise low voltages to the CPU. They're in your phone, your car, the giant servers that run the internet, and even in spacecraft where every single watt of power is mission critical. They are truly the foundation of modern electronics. As Professor R.W. Erickson over at the University of Colorado puts it, the ideal goal is always that perfect 100% efficiency. And while we can't quite cheat the laws of physics, getting up into that 90 to 95% range is what makes all of the high-performance, low-power gadgets we depend on every day possible.
And all of this leaves us with one final thought. We keep demanding more and more from our electronics. Everything from AI running on our phones to electric cars that can charge in just a few minutes. All of it comes down to being able to manage power better. So the next time you pick up your phone, just take a second to remember the silent, incredibly efficient work of the DC-DC converter inside, and ask yourself, what will the next great leap in this technology make possible?
Thanks for watching, and please like, share and subscribe for such more content and appreciation. Make sure to comment your questions and